Hi everyone, welcome to CS188 section 5, and today I'll be going over the solutions. So the first problem is on MDPs, and it's going to be a small version of blackjack. So I'll assume that you've read the statement, and if not, take a second, pause, and read it. Okay, so what they want us to do is what is the transition function and what is the reward function for this MDP. So the written solutions have it written out in terms of equations in terms of T and R, but I'm going to draw it visually, and from that you would be able to get the answer in the solutions PDF. So first let's write down the states. So we have, let's see, state 0, state 1, sorry, there's no 1, not possible, state 2, state 3, 4, 5, and done. Okay, so now we're only gonna, there are two actions we can take. From each one, we can either draw, and it'll either be a 2, 3, or 4, or we can stop, and the score is the total score. So if you stop, it's going to be pretty simple. So if you stop, the transition probability, so T, doesn't really matter what the arguments, you always will stop, and the reward of S comma A comma S prime will simply equal S, which is your current state. So if I have 3 total and I stop, I'll get a reward of 3. So now let's only draw Let's only draw what happens when you draw for cards. Okay, so let's start at 0. So I can either draw a 2 or 3 or 4. So that means I'll either transition to a 2, a 3, or a 4. And for all these, I'm not going to get any reward. It's only when you do stop that you get a reward. And the probability is going to be 1 over 3, 1 over 3, and 1 over 3. Okay, so now let's consider 2, from state 2. So I can, let's see, draw a 2, a 3, or a 4. So if I draw a 2, and I end up here, and that's also 1/3 probability. If I draw a 3, and about 5 with a 1/3. And if I draw a 4, I go over and I'm done, so 1/3. Now if I'm at 3, there's a 1/3 chance that I end up in 5, and then at the other 2 cards, 3 and 4, would put me over. So it'd be a 2 out of 3 chance. Now if I'm in 4 and I draw, I'll always go over. So that's a 1 probability chance, and if I'm in 5, that's a 1 probability chance. So now I've basically defined T and R for all possible states and actions. So now let's move on to number 2. Let's fill in the following table of value iteration for the first 4 iterations. Okay, so for V0, we always initialize our values to 0. So these will all be 0. Now we need to apply the value iteration update. So let me write this at the very top. So Vk plus 1 of S gets updated to be the max over actions, sum of all next states, T of S comma A comma S prime times the reward I would get plus gamma times the value. Okay, so now let's consider the next iteration. So we'll start in state 0. So I need to consider each action individually because there's a max, and then I'll sum over all possible next states, the transition probability times the reward plus gamma times V of S prime. Okay, so first let's consider if I draw. Well, if I draw, I get no reward, R, and the values are all 0 for where I end up, so that would be 0. Now if I stop, I get a guaranteed reward in my current state, which is 0. So no matter what, I'll be 0. Now let's consider 2. So 2 is also the same. If I draw, I get no reward, and the states I end up in are 0. So no matter what, the sum will be 0. So drawing will be 0, but if I stop, I get guaranteed 2. So this will be 2. So this logic also applies to 3, 4, and 5. This is because none of the values have been updated. They're all 0, and I get no reward from drawing. So stopping is always best. Now let's consider V2. Iteration 2. So now let's start at state 0. So now this is going to be different. So if I stop, I'll get a 0, but if I draw, it's going to be 1/3 times the value of the state that I end up in, because I get no reward, and gamma equals 1. So it's going to be 1/3 times 2 plus 1/3 times 3 plus 1/3 times 4, and that'll give me 3. So that's what happens if I draw. Now let's see what happens if I'm in 2 and I draw. So there's a 1/3 chance I'll get 1/3 times the value of 4, which is 4, plus 1/3 times the value of 5, which is also just 5 because there's no reward, and then 1/3 that I go over. So 5/3 plus 4/3 is 3, and that's better than just stopping. So I'll take that. Now let's consider state 3. So I have a 1/3 chance of going to 5 and 2/3 chance of getting nothing being done. So that's a 5/3. Or if I stop, I'll get a 3, which is better. So I'll just stop and I'll get 3. And 4, I would always go over. So drawing will give me 0. And if I stop, I'll get a 4. And same with 5. Drawing would get me nothing, so I would just choose to stop and keep my score. Now let's consider V3. So let's start in state 0. So we pretty much know we're not going to do stop because we get 0 from that. So now we just need to see what draw gives us. So it's 1/3 times the value of 2, which is 3. So 1/3 times 3 plus 1/3 times 3 plus 1/3 times 4. That's all the places I can go from 0. And that, if you calculate it out, will give me 10/3. Now let's go to 2. So if I'm in 2, is a 1/3, I go to 4, and what's the value of 4? Well, it's 4. 1/3, I go to 5, the value is 5, and 1/3, I'm done, which gets me none. So if I calculate this out, 4/3 plus 5/3 is 3. So that still remains the same. And if now I'm at state 3, there's a 1/3 chance I go to state 5 and I get a value of 5, and 2/3 chance I'm actually just done. So that's 5/3, which is less than 3. So I'll just stop, and it'll be the same for 4 and for 5. Now, if you do V4, you'll actually find the exact same values as V3, the same exact calculations I did. So we'll just fill that in. Okay, so now question 3. So you should have noticed that the value iteration converged above, which we did because iteration 3 and iteration 4 were the same. So what is the optimal policy for the MDP? So to do this, and we're keeping track of everything in terms of values, we need to do policy extraction. So we basically need to do value iteration, but we need to do an argmax. What's the best action? So we actually did this when we calculated V3, but we can do this again. So when I'm in state 0, if I do nothing, if I say done and I stop, I'll get value 0. And if I draw, then I got this 10/3 value. So that means I'll draw. Now in state 2, if I stop, then I'll get a 2. But here I see I got a 3, so that means I must have drawn. So I draw. Now I'm in 3, and I see that the optimal value is also 3, which I get from stopping. And when I'm in state 4, I see that the optimal value is 4, which I get from stopping. And when I'm in state 5, the value is 5, which also means that I stopped. So this is the optimal policy. So now they want us to perform one iteration of policy iteration for one step of this MDP, starting from the fixed policy below. So what do? Well, first let's write down the policy iteration equation. So the value of pi I of s is the sum over all next states, t of s comma a comma s prime, where a actually comes from s, our current policy. Sorry for the writing. And then the reward is r of s comma the action our policy says, comma s prime, plus gamma times our current estimate of the value. And remember that in policy iteration, we actually need to run this mini value iteration to convergence. So these are VKs. So our values get updated just like we did above, but for our given policy pi. So now let's look here. So they want to know what's the value when we run pi I to convergence. So this seems like a difficult problem. We need to form the above table in 2 and just run it with this policy pi I until convergence. But this problem is fairly simple, and we can take advantage of its structure. Okay, so let's start at the stops, because when we're in a state and we stop, we know what value we get. So in state 4, if we stop, we get a 4. And if we're in state 2 and we stop, we get a 2. Now let's start at the back, because we know those usually tend to go to done states. So if we're in state 5 and we draw, we know that we're always going to go over, so we get a 0. Now, if we're in state 3, we could end up in 5, done or done, based on what we drew in 1. Well, in state 5, we also draw according to this policy, so we'll always get 0. Now, if we're in state 0, we can either go to state 2, state 3, or state 4. So if we go to state 2, we'll end up getting a 2, state 3 will get 0, state 4 will get 4, and we have 1/3 probability of each. So it's going to be 2 over 3 plus 0 over 3 plus 4 over 3, which will give us 2. Okay, so now that's just the first part of policy iteration. Now we need to do policy improvement, which is basically extracting the best action given our current values. So first, let's just start at the end. So we'll start with state 5. So what we can see is that we can either take the action of draw, which gives us 0, or if we stop, we'll get a 5. So we'll see that the policy will update to stop. For 4, we can consider stop, which will give us 4, or we can consider draw, which will always put us over and give us 0, according to our current estimate of the value. So we will also choose to stop. Now in 3, we need to consider the policy extraction. So we first consider stop, which will give us 3, or we can consider draw, which would either get us to 5, which actually has a value of 0, or it'll put us in the done state, which is also 0. So we'll actually choose to stop. Now, if we're in state 2, if we stop, we'll get a 2. And if we draw, according to our current estimates of the value, we would extract either a value of 4, or a value of 0, or we would go over and we would be done. So the probability of going to state 4 and getting 4 is 1 over 3. Probability of going to 5 is 1 over 3. And probability of being done, which is also 0, will be 1 over 3. So we would actually get 4 over 3 from that. So we can either get 4 over 3 from drawing or 2 from stopping. So we'll actually still choose to stop. Okay, so now we're in state 0. So we can either stop and get a 0, or if we draw, we'll get 1 over 3 times the value, which is 2, plus 1 over 3 times the value, which is 0, plus 1 over 3 times the value, which is 4, and that'll give us 2. So we'll actually choose to still draw. And that's it for the MDP question. Okay, so now we're going to talk about a reinforcement learning problem. So again, we're going to consider our favorite example, Greater World, and we are going to try to use TD learning and Q learning to find the values in these states. Now remember, we don't actually know the transition probabilities or the rewards, so we have to take actions. So here they give us 4 observed transitions. So what are these? So we start in state B, we go east, and we end up in C, and we'll get a reward of 2. We're in C, we go south, we end up in E, we get a reward of 4, and there are 2 more. So they tell us that the initial value of each state is 0, and assume that gamma equals 1 and alpha equals 0.5. So first, let's write down the TD learning and the Q learning equations, which are going to be useful for both 1 and 2. So for TD learning, we're going to get a sample, which is the reward, plus gamma times the value of where we end up. And then we update the value of that state to be 1 minus alpha times the value, the old value, plus alpha times the new value sample. And I'll write down the Q1 later. Okay, so what are the learned values from TD learning after all 4 observations? So we're going to be updating the values, so let's keep track of them. So A, B, C, D, E, and they all start out as 0. Okay, so we're just going to go observation by observation, use these 2 equations, and update our values. So first, we start with the B east C2. So the sample is going to be the reward we got, 2 plus gamma, which is 1, times the value of C, where we ended up, which if we look at our table is 0, so that equals 2. And now we update V of our start state B equals 1/2, which is 1 minus alpha, times the old value, which is 0, plus 1/2 times our sample, which is 2. So that means we're going to update B to be 1. Okay, now let's do the next one. So we get a sample from C to south to E with a reward of 4 plus gamma times the value where we end up with E. Look at our table, it's 0. Then we update our value for our initial state, C, which equals 1/2 times the previous value of C, which is 0, plus 1/2 times the sample, which is 4. So this will be 2, and we update C to be 2. Now let me make some room. So now we get our next sample. So C east A6, so we get a reward of 6 plus gamma times where do we end up, A, which is the value of 0. Then we update V of our initial state, which is C, which equals 1/2 times our old value of C, which here is actually going to be a bit different. It's actually not 0, it's 2. Then plus 1/2 times our reward is 6. So now we update C to be 4. Okay, so now we're on our last one. So we get a sample. Our reward, as we look here, is 2 plus gamma times the value where we end up, C, which is 4. Then we update the value of where we started, VB equals 1/2 times our current value, which is 1, plus 1/2 times our sample, which is 6. So now we update VB to be 3.5. So our final answer for the values are 0, 3.5, 4, 0, and 0. And that's it for TD learning. So now let's do Q learning. So if I write the equations up here, Q learning, it's going to be the exact same almost. So our sample is going to be our reward plus, it's going to be gamma times the value, which is the max over A prime of Q of S prime comma A prime. Sorry for being very squished. Then we update our Q value of S comma A, which is 1 minus alpha times our old estimate plus alpha times our new estimate. Okay, so let's do 2. So we can't actually write, well, it'd be hard to write out all pairs of S comma A. So I can just look at my observations and note that I'm only going to update Q of S comma A for my observations. So what is that going to be? That can only be Q of B comma east and Q of C comma south, and lastly Q of C comma east. And we initialize all of these to be 0. Okay, so now let's start things out. So we get our first sample, BEC2, so reward of 2 plus gamma times the max over all Q values and where we end up, which is C. Well, we look here, everything's 0, so it's going to be 0. Now, what is Q of B comma east going to be? It's going to be 1/2 times the previous value, which is equals 0, plus 1/2 times the current value, which is 2. So we update that to be 1. Now we get our next sample. So C south E4, we get a reward of 4 plus gamma, which is 1 times the value, the max Q value of where we end up. So we end up in E. We see that all the Q values are 0, so this ends up still being a 0. Then we update our Q value, Q of C comma south. So this equals 1/2 times the previous value, which is 0, plus 1/2 times our reward, which is 4. So now update this to be 2. Okay, now we get a new sample. So it's going to be the reward C east A6 will be 6 plus gamma times the value of where we end up, or the max of the Q values of A where we end up. So A, all the Q values are 0, so it's still going to be 0. Now we update Q of C comma east. So it's 1/2 times the previous value, 0, plus 1/2 times the reward we just got, which is 6. So this becomes 3. Now our last sample, we get sample equals the reward we get, B east C 2. So 2 is our reward. Plus gamma times the max of all the Q values where we end up. So we end up in C. Now for C, what's our maximum Q value? Well, it's actually 3. So 2 plus 1 times 3. So this is a little different than the previous ones. Now we're going to update Q of B comma east. So this equals 1/2 times the previous value, which is actually 1, plus 1/2 times our current value, which is 5. So what does that give us? That'll give us 3. So then I cross that off and we get a 3. And now we're done.